All right, we are continuing with the three-dimensional kinematics. So let me again repeat. So this is quite similar to one-dimensional kinematics. But now all the relevant kinematical quantities are vectors in three-dimensional vectors. As a result, I need to use the unit vector. Well, I need to use the vector notation at least. Do I need to use a unit vector notation? No, but that's actually one possible choice. But we define everything as vectors. So position is a vector defined in the usual way. It's basically the position relative to the origin. Displacement is the difference between the final and initial vectors for a certain motion between an initial and final moment. Let me erase this. P actually represents the particle. So when a particle moves from an initial location to a final location, displacement can be taken as the final position relative to the initial position, but this corresponds to the vector difference of these two position vectors. All right. And then we have, continuing with this, we have average velocity. Let's say in a time interval delta t, again, it's the same. So that's the difference between final and initial times. So it's an average velocity within an interval always. Just keep this in mind. So we just show this by this notation. It's a vector, so therefore I'm putting an arrow. It's an average quantity, so therefore I'm putting this bar in here. So that's basically the displacement divided by delta t. Okay, so this time I cannot draw any graphs because there are three different positions in here. Perhaps I can draw three different graphs or and then relate the average velocity to the slopes of some lines drawn in those graphs, but probably that's not necessary in here, right? That's something that you can easily do. So, and then instantaneous velocity. All right. So the instantaneous velocity is again a vector, but there's no bar in here, is basically the time derivative of the position. And we know the meaning of this. That's basically the limit of the average velocity over a very short time interval when the time interval goes to 0. Okay. So all of these quantities can be expressed in terms of the components as well. So V has these components, Vx, Vy, and Vz. R has components X, Y, and Z. So when I take the derivative, I take the derivative of the components. dz over dt. Okay, let me just do it like this. So that's the vector equation in here that I have written above. So it's the same as this equation, but this time it's written in unit vector notation with components spelled out, let's say. But if the left-hand side is equal to the right-hand side, then all components must be equal to each other. So that means the x component of the velocity is equal to the time derivative of the x component of position. Y component of the velocity is the time derivative of the y component, and so on. All right, so let me at least write everything clearly at this stage. So as a result, if you look at the components only, so the 1D kinematic relations are basically still valid. Relations for components are still valid. Okay, so I don't know how to describe this thing, but for example, this is a particle, let's say it is moving like that. I just look at the shadow of that particle on the x-axis, right? This is a shadow, it's a projection. Think of it as a shadow, but the shadow does a one-dimensional motion, right? So you can investigate the kinematics of that shadow, and the kinematics of the shadow satisfies the usual one-dimensional kinematic relationships, okay? So as a result, by knowing 1D kinematics, you can easily describe the three-dimensional kinematics of the object, right? That's what I'm saying. So you don't have to do a full vector algebra with the unit vector notation. You can just work with the components only. Okay, so it's going to continue like that. So as a result, we have the average acceleration. They say over time interval, let's say from Ti to Tf, but yeah, from Ti to Tf again. But usually people just call this as the average acceleration. So that's the change in the velocity divided by delta t. So it's whatever. You can write it in explicitly in terms of the final and initial velocities, perhaps. But the important quantity is the instantaneous velocity. So that's the time derivative of the velocity. Sorry, instantaneous acceleration, right? It's the time derivative of the velocity, which is the limit of the average velocity, average acceleration. Probably I have made many mistakes in the previous hour, so sometimes I cannot notice the mistakes. So instantaneous acceleration is defined in the usual way. So it's the same thing again. So acceleration is the time derivative of the velocity. So therefore, it's the second time derivative of the position. Okay. So as a result, we have these three quantities, the position, velocity, and acceleration. So basically, let me say it like this, in Newtonian dynamics, these are the quantities that we are interested in, especially acceleration, but the other quantities may also depend on velocity and position as well. All right. I can continue with the derivatives, perhaps. I can describe the derivative of the acceleration and things like that. Nothing prevents me from defining them. But if you want to do dynamics, then we stop at acceleration because that's the only thing that we need. Okay, we know this. All right, there are some other things that I actually wanted to mention, but let me just mention this. So let's say it like this. This is the reference frame, X, Y, Z, right? So this is the particle that I'm looking at motion. So this particle moves around, right? So as a result, you can think that it is drawing a curve on the in the space. This curve is called trajectory. And sometimes orbit, especially if the trajectory is, this is periodic motion where the object comes back to the same point and passes with the same velocity. In periodic motion, it's also called an orbit, especially in planetary motion, of course. So in all of these cases, let's say it like this, the instantaneous velocity is always tangent to the trajectory. All right, let's say it like that. V is always tangent to the trajectory. right? The reason is that the displacement is, of course, is along the trajectory, is tangent to the trajectory. So therefore, the velocity should also be, right? So at every point, the velocity would be like that. And the second thing is, well, acceleration. So you might also have some acceleration, but the acceleration does not need to be in a certain direction. So it might be making some angles. We will see later that if it is curved, if the trajectory is curved, then the acceleration has a component towards the center of curvature in a way. So as a result, this is going to have, I mean, at that point, for example, the acceleration is going to have a component along that direction. But if it is slowing down, we will see that it is going to be directed like that, all right? In any case, so it might be pointed like that or whatever, like this, or it might be parallel to or anti-parallel to the curve, right? So there might be many possible directions, okay? So again, let's remember, S is the speed is the magnitude of velocity. Okay, so sometimes we ask the question like, does the speed increase or decrease? In everyday life, for example, this is some kind of a valid question that we are interested in. So the car we are in, for example, is it speeding up or slowing down? Speed up, slow down, right? In Newtonian mechanics, this is usually not important. We will basically see some of the reasons later why we are not interested in the speed, but we are interested in the velocity. So the speed may change, but what's important in here is whether the velocity is changing or not, right? In any case, but there's this kind of a thing in here. So it appears that if the velocity, let me say it like this, if the angle between the velocity and the acceleration is, I'll show this later, if the angle between the velocity and the acceleration is less than 90 degrees, then the speed increases, so the object speeds up in a way. On the other hand, if the angle between them is bigger than 90 degrees, right? Like that, for example, in that case, it appears that the object is slowing down. So I'm just going to give this as a statement in here. I don't want to prove this in here. Because if I do it, then you will get confused. I know that, but at some later point, I'm going to show you this. So as a result, you can decide on whether the object is speeding up or slowing down by just looking at the relative direction of the acceleration and the velocity. Basically, if the acceleration has a positive component along the velocity direction, then in one-dimensional motion, this corresponds to the fact that both acceleration and the velocity are parallel to each other. This corresponds to speeding up, so that is that situation. And so if the acceleration has a negative component, so that means this negative component, this component is opposite to the velocity. In that case, it slows down, right? So in one dimension, of course, we also have the same relationship, but in one dimension, there are only two possibilities. So acceleration and velocity would either be parallel to each other or anti-parallel. So you get speeding up or slowing down in that case. Here, we have more possibilities, but by just looking at whether that angle is bigger than or smaller than 90 degrees, you can have these two situations. And there's a very interesting situation where the acceleration is perpendicular to the velocity. This is the case when the speed is either a maximum or a minimum, or it's just constant, right? I'll talk about this later, right? Okay, so in any case, let's then talk about the constant acceleration motion. I'll just draw it, first of all, vectorially, and then I'm just going to write down the algebraic equations, right? So let's say that initially the object has, I started with the yellow color for the velocity, so let's just do this. So suppose that I have an object with a velocity, initial velocity v0, and let's say that the acceleration is along this direction. In circular motion, yeah, the speed is constant. Yeah, in that case, the acceleration is perpendicular to velocity. Okay, so constant acceleration motion. I'm looking at the situation where the velocity is, initial velocity is like this, and the acceleration is like that. So that would mean that if the acceleration is constant, at any later time, if the velocity is like that, right? Just look at the change in the velocity. So that's delta V. Delta V. That delta V vector should be parallel to the acceleration. And if the time is positive, all right, if the time is later than the initial time, in that case, it should be basically parallel to the acceleration. So that's a times delta t. All right. So in the case of constant acceleration, we have this formula valid all the time. And so as a result, I can just continue with this. So I don't know, I can look at all the other times in here. So at a later time, perhaps the velocity would be like this. So let me call this as v prime, for example. At much later time, the velocity would be like that. So that's v double prime and so on. So in all of these cases, the changes in the velocity, they are always in the same direction. Okay, so I can then continue like that in here. All right, so I'm just going to do it with a simple situation. So at time t equals 0, let's say this is time t equals 0, let's say. And let's say that this is the velocity at time t, right? Time t then. So in that case, I think I'm going to use white color in here. So, all right. So this delta v in here is basically acceleration times t. So that means v minus v0. So that's delta v. That's equal to acceleration times t then. So therefore, the velocity can be expressed as v0 plus a times t. Right, I mean, we are using the usual two vector operations, right? This is the multiplication of a vector with a scalar. That's the vector addition, okay? But if you just look at the components, these are just the usual, I mean, there's nothing to be afraid of in here. Okay, so I can also continue with the displacement. So what's the displacement? Let's see. What's the displacement? Delta R. Delta R was the average velocity multiplied with t. Sorry about this. No, I'm not doing this. Sorry about that. So yeah, I don't have a formula of the average velocity yet. All right, I'm just going to do it like that, all right? So I just noticed that in here, the time derivative of the velocity is, I can do the same kind of a trick. So that's 0 plus acceleration multiplied with the time derivative of t is equal to 1. So that's equal to the acceleration. So I'm just going to do the same thing with the position. Okay. So what I do is I take the antiderivative, right? Let's say by taking antiderivatives, I can easily say that the position is equal to the initial position plus the initial velocity times t plus 1/2 of a times t squared. Right, it's the same formulas. We can use the same kind of arguments, but I think the graphical argument is not straightforward in here because you have to use the graphical arguments for each component separately, but I don't want to do this. Where did the constant of integration go? This is the constant of integration in here. Okay. So in all of these cases, all right, R0 is the initial velocity, initial position, and V0 is the initial velocity. And obviously, R and V are the final quantities. Let me quickly write it down like that, all right? Final velocity in here. A is the acceleration, it's the initial, final, doesn't matter. So it's the acceleration, but you can think of it as one of the final quantities as well. And then we have the time. The time is a scalar now, but all the other quantities are vector quantities. Now I can define all the other ones, relationships. So the average velocity, for example, that's delta R divided by delta T. You can do the calculation, but at the end, you are going to see the same thing again in here. So it's the arithmetic average of the initial and the final velocities, okay? So as a result, I'm just going to write down this relationship again. And then there's one final relationship. I can write this thing down. So that's basically V dot V minus V0 dot V0. That's equal to 2A dot delta R. I don't want to show you how I obtained this because that part is not relevant. But let's just say that, I mean, these are the same relationships that I have written down in the case of the constant acceleration motion in one dimension, right? The only difference in here is that all of these quantities in here are vector quantities. So as a result, these three equations, 1, 2, and 3, these are vector equations. The fourth one is a scalar equation because somehow it involves the dot product of two vectors in it. Okay. So as a result, the three-dimensional kinematics is the same thing as one-dimensional kinematics. However, there's something in here, right? Especially, I'm just going to write it down like that, right? We can write down the X, Y, and Z components of equations 1, 2, and 3. Okay. All right. Let me answer that question later. So, for example, just take the equation 1, all right? I'm just going to repeat the equation here. So that's R is equal to R0 plus V0t plus 1/2 of AT squared, right? So I can actually write this thing down as an equation. I just look at the X component of that equation, Y component of that equation, and the Z component of that equation, and write them down separately. So let me use a yellow color for that. So I can write X is equal to X0 plus V0x t plus 1/2 of AX t squared, right? Here, x0 is the x component of the initial position. v0x is the x component of the initial velocity v0. ax is the x component of the acceleration, all right? So I can take the x components of the vectors that appear in here and write down the corresponding equations. All right, let me do the same thing in here. So that's z0 plus v0z plus 1/2 of az t². What I'm trying to say is that you don't have to write this thing down as a vector equation. Just forget about the vectors and then look at the components. So that each component is a constant acceleration motion. And so as a result, for each component, you can write down the constant acceleration formulas, right? But of course, for the x component, you have to write down the x component of the acceleration. For the y component, you have to write down the correct component, okay? That's another way of doing this constant acceleration, writing down the constant acceleration formulas in 3 dimensions. Okay, let me do that one more time with this, with the velocity. So Vx is equal to V0x plus Ax times t, etc. All right, let me just write them down and then I don't want to continue. Yeah, let me write one more equation. Okay. So there's this average velocity rule. So that was the 3rd equation. So average velocity was equal to the arithmetic average of the initial and final velocities. All right. Let me not write them down, all right? But the last equation, v dot v and minus whatever, let's say whatever in here, because it appears that by using the fact that the x component of the motion is a constant acceleration motion, I can write down the 4th equation in terms of the x component only. So this is valid. For the y component, I can also write down the same thing, right? And for the z component as well. All right, it's basically the same equations. I just changed all x's with y's and z's, all right? I mean, it appears like there are too many equations in here. So it appears that, so the last equation that I would write in terms of the dot product is actually, is a little bit, it's actually, it doesn't contain too much information. So it appears that these 3 equations by themselves hold. But if I write them in terms of the dot product, it's basically the sum of these 3 equations, right? There's this kind of a complication in there. So in any case, I mean, for most of the problems, typical problems that we meet, like the projectile motion and things like that, we usually use these equations, the component forms. So as a result, probably should concentrate on that part only, right? So the essential idea in here is that if you have a constant acceleration motion in 3 dimensions, then all components of that motion will be a constant acceleration motion. And as a result, you can investigate each component as a constant acceleration motion and then solve the problems there. The only complication in here is that sometimes, I mean, there are problems where something special is happening along the x direction, but we are asking for a quantity along the y direction, for example. So as a result, you have to combine them, but that's the only difficulty in here. Okay, so I spoke too much, so I just want to solve one problem in here. So this is just an example. It's an unusual example because this is a problem which is just asked just like the one-dimensional problem. So I just give the initial position and final position and things like that. But I basically ask the quantities as vector quantities so that you have to provide them in with unit vector notation. So the situation is like that. So we have an x-axis and a y-axis, An object starts its motion from the origin. Initially, it is moving like that. So I'm just going to show it like this. So that's the initial velocity, V0. And eventually, it ends up at that point, which has coordinates of, let me write it down like that. So I think I need to look at this. So the coordinates are 75 meters and minus 100 meters, right? So it's a two-dimensional constant acceleration motion. Okay, let me quickly read this and then write. So a particle starts its motion from origin, moving along let's say with initial velocity along plus y with speed, what, 10 meters per second. Okay. Under constant acceleration, it reaches the point A, right? Point A in t equals 5 seconds. Right, let me just write it down like that, okay? So in 5 seconds, it reaches to that point. So as a result, the trajectory is something like that. So let me use a pink color for that. So it starts moving like that. And then whatever, it just does this and then passes from that point, right? It's not a perfect shape. So this trajectory should also look like a parabola, but yeah, I cannot draw it. So as a result, imagine this as a parabola, right? I mean, I don't know much about the trajectory, but I know that this is a constant acceleration motion. So as a result, we're just going to use this information. So the questions are, what's the acceleration? Part B, final velocity. All right, part C, average velocity during that time interval, but find it by using two different methods. Okay, and part D is, let's see, find the position when the object is farthest along the y direction, right? When the object is farthest along the positive plus y direction. Okay. All right. So in any case, I mean, usually for two-dimensional constant acceleration motions, we just separate the motion into these components, x and y components, and then we just investigate the components separately. Here, we don't need this. We don't need to do that. So as a result, this is kind of exceptional. But I'm solving this on purpose to actually show you that, this is not different than the problems that we have solved in the one-dimensional motion case, except that I need to use unit vector notation to express these quantities, position, velocity, and acceleration, right? That's it. Okay, so the given quantities, so let me do it like that, right? So the given quantities, so the initial velocity, so first of all, initial position. Initial position is 0, so it's at the origin. So that's the origin. All right. What's the initial velocity? It is 10 meters per second along the y direction. So therefore, this is 10j meters per second. Was it 10? Yes. All right. I have the direction in here. Yeah, well, I use the unit vector notation. So that's the quantity. So therefore, there's a unit in here. All right. Everything is fine. Then we have the final position. Final position is 75I minus 100j. And the unit is meters. So I usually write down the unit like that. So the unit is multiplied with this whole expression. So as a result, I'm using parentheses in here. So in part A, we are asking for the acceleration. In part B, we are asking for the final velocity. Part C, we are asking for the average velocity. All right, forget about part D now. All right, we would like to solve this problem. And I think I can solve the problem part A easily by using this equation. So R is equal to R0 plus V0 times T plus 1/2 of A times T squared. Sorry about that. We also know what the time is. Time is 5 seconds, right? So I know the time, okay? I don't know the acceleration. That's the one that I need to find. I know the initial velocity. I know the initial position. I know the final position. So therefore, this is an equation with one unknown, one vector unknown. So I can solve it. So final position, right? This is initial position. Initial velocity is 10j. I multiply it with 5. Sorry, let me shift. And then acceleration is, I don't know what acceleration is, but I need to multiply it with 25 divided by 2. So I think I need to multiply it with 2 and then divide by 25. So I cannot do this quickly, so let me do it in the long way, all right? Sorry about this. So this is 50 multiplied with 2 is 100. And then I have 25a in here. Let's see, divide by 25. So that gives me 6i minus 8j. That's equal to 4j plus a. All right. So therefore, the acceleration is 6i minus 12j meters per second squared. Okay. I could have solved the problem by components. I could have solved the problem by components. I would reach to the same result, but in any case, that's the correct answer. So in any case, when I asked for the acceleration, since acceleration is a vector quantity, I expect a vector answer. So as a result, I mean, an answer like, for example, the 6 squared plus 12 squared is not enough, right? That is incorrect. That only gives the magnitude of the acceleration. You have to also give the direction in here. And the best way to specify the direction is by using the unit vector notation, all right? I mean, if you can compute the angle somehow, and this angle is simple, you can also give the magnitude and the angle information as well. But in any case, in this problem, it is easiest to specify the acceleration by using the unit vector notation, okay? Part B, what's the final velocity? Final velocity is initial velocity plus acceleration times t. Initial velocity is 10j. Acceleration is 6i minus 12j. Time is 5 seconds, so therefore we get 30i. 5 times 12 is 6 minus 60, so you get minus 50j meters per second. So that's the final velocity. All right, part C. What's the final, average acceleration? I can use these two formulas. One formula is basically the arithmetic average of the initial and the final velocities. So that's a constant acceleration formula. Right, that formula is only valid if the motion is a constant acceleration motion. Let's continue. So that's 30I minus 50J. Initial velocity was 10J. Divide by 2. So I'm just doing usual vector algebra, all right? So it's basically multiplication and addition. We don't have these dot products and cross products entering in here. So 30I, so that's 15I minus 40J divided to minus 20J meters per second. So that's the average velocity. So it's the arithmetic average of the initial and final velocities. So the other one is the definition of the average acceleration. So that's the displacement divided by the time. So of course, that's R minus R0 divided by T minus 0. The position was 75I minus 100J. Initial position is 0. Final time is 5, whatever. So I need to divide this by 5. Well, I just write down copy the previous answer, assuming that I have done this correctly. All right, so that's meters per second. And then I say that, well, both of them are equal, so that's nice. Okay. So I think let me quickly do this, the last part in here. So this is basically saying that when Y is max, what is delta R? Right? That's asking this question. The problem in here is that there is a condition in here, and that condition happens along one direction in here. So I need to look at this condition in here. I know that when the Y component of the position is maximum, velocity along that direction has to be 0. So that's my condition then. So as a result, what I would like to do is I just write down this condition and solve for it. So that's the equation in here. So let me call this as T1 in here, let's say. So that's a different time. So final Y velocity is equal to 0. Initial Y velocity was 10. Y component of the acceleration, I forgot. It was minus 12. So that's minus 12. So as a result, we find the time from here. It is minus 10 over 12 seconds. So it's positive, sorry about that. And then we find the final position from here. So that's by using this formula. And I'm going to check if I have already computed this. If I don't, then no, I didn't compute this. So as a result, let me just say ... in here. So it's just a straightforward calculation, but with a strange number, obviously. Okay, so in any case, so that's how we solve this. I have just done this to illustrate the fact that the three-dimensional kinematics is really one-dimensional kinematics with all the quantities are replaced with the vectors. And we can do the usual vector algebra in here, right? That was just an opportunity to do vector algebra, and I have caught that opportunity and done this. But tomorrow we are going to see the projectile motions. So as we are going to see there, most of the time we will just be looking at the components of each motion, and that would be enough. Okay. Let me stop the recording now.